let's look at this second example. When does this series converge? Now remember, every series converges at its center, but could it converge at other values? So again, because we see a factorial, that's always good for the ratio test. So I want to take the limit as n approaches infinity of, remember, the ratio of the n plus 1 term divided by the original, which means I'm going to flip and multiply. Okay, this is where you have to be really careful about how to simplify. So remember, n plus 1 factorial is n plus 1 times n factorial. So those go. So you're left with n plus 1 on the denominator. And then because you have n plus 1 and n plus 1 squared, you should be able to reduce that. And that reduces, and that just leaves you now an n plus 1 on top. So let's see, we've gotten rid of that. Now, what about the 2's? I can reduce that to just 2 in the denominator. These x's I can reduce to just x. Again, you really need to know your laws of exponents, keeping the base, subtracting the exponents, and being really careful about that. So we have the limit as n approaches infinity of the absolute value. Let's see, what do I have in terms of x? So I have x over 2, and then I'm going to put all my n's, so I have n plus 1 on top and n squared on the bottom. Keep in mind, we're looking as n approaches infinity, not x, but n. So what happens to n plus 1 divided by n squared as n approaches infinity? That limit goes to 0. And 0 times anything is equal to 0, which is always less than 1. Remember, using the ratio test, it converges if this limit of the ratio of these n plus 1 term to n, if that's less than 1, then this converges. It did not matter at all what x equals to. So no matter what x is, the limit always is 0. So therefore, the series converges for all x, and so our domain is all real numbers. Okay, so we've now looked at a case where it had a radius of convergence and we had to check the endpoints. Now we see that it could be all real numbers. Let's look at the third example. When does this series converge? Again, I see factorial, so I want to use that ratio test. Since we don't have a fraction, I just have the n plus 1 term divided by the nth term. Okay. I should be able to reduce that. Remember again that n plus 1 factorial is n plus 1 factorial is n plus 1 times n factorial. So what that's going to leave me here is n plus 1 on top. These have the same base, so I can keep the base and subtract the exponents. And so that's just going to leave it to the first power. So what I have here is the limit as n approaches infinity of x minus 4. And again, it's really a good idea to separate your x's and your n's times n plus 1. So again, looking only at the n value, as n approaches infinity, what's that going to limit be? Infinity. Again, it's really not dependent on x, because if you have something really huge multiplied by x, it's not going to get small. Okay, it's going to be infinity. That is never less than 1. So does that mean that it never converges? No. Remember that every series converges at its center. Meaning, what would happen if x was equal to 4? Then you would have 4 minus 4, which is 0, and you would get 0, which is less than 1, and it would converge. So this only converges when x is equal to 4, so you could leave that as your domain, or again, you could write it in interval notation. Let's just practice a little bit more. Again, I would encourage you to see if you could stop the video and try these problems on your own and see what you get. So again, I'm going to use the ratio test. So since I am taking the absolute value, this negative is going to go away, right? The absolute value of -1 is +1, so I'm not even going to write that down. So I'm going to have x to the n plus 2, that would be the next term, divided by 3 plus the square root of n plus 1, multiplied by, of course, that reciprocal. First of all, you cannot cross out those 3's. Those have an addition that's not a factor. But you can reduce the x's, and that would leave you an x on top. So let's see, we would have the limit as n approaches infinity of x multiplied by this. Again, separating those x's and n's should help. Okay, so again, we're looking at the limit as n approaches infinity. What's going to happen as n grows really large? That 3 is going to become inconsequential, and since you have the same degree divided by the same degree with the leading coefficient of 1, that limit is going to be 1. So again, we have the absolute value of x, that's what's left, and it will converge if that absolute value of x is less than 1. So we know we have this radius. The question is do we include our endpoints? So just like on the first example, we have to check our endpoints. So I'm going to let x equal to -1. So now I have to go back and put that -1 back in there, and everywhere there is an x, I'm going to let that be -1. And before you figure out like what test you're going to do on that series now, you need to kind of clean it up. So what happens when I multiply? I have the same base. What can I do with those exponents? I can add them. So this is -1 to the 2n plus 1 over 3 plus the square root of n. Well, what kind of numbers do you get? Is this going to go back and forth between -1 and +1? Well, let's just see. Let's just kind of write out the first couple of terms. When n is 1, you're going to get 2 plus 1, which is 3. So you're going to get -1 cubed over 3 plus the square root of 1. So that's when n is 1. When n is 2, you're going to get -1 to the 5th power. And when n is 3, you're going to get -1 to the 7th power. And so forth. So hopefully you can see you're always going to get odd exponents, which means this is always negative. This is not an alternating series. So you cannot use the alternating series test. So since we know this is always negative, we actually could write this series as -1, just leave it as -1 over 3 plus the square root of n. That's how that series is simplified. So I can't use the alternating series test. How about a comparison test? Let's compare it to 1 over the square root of n, which is a p-series, where p equals 1/2, which is less than 1, which diverges. So if I use the direct comparison test, remember if this diverges, I have to compare this by an inequality. Right? So if this diverges, so if this is really big, then I need what I'm comparing it to be even bigger. Is that going to be true? Well, I don't think so, because you're going to have a negative greater than a positive. That could be problematic. But wouldn't it be nice if there was a negative there? Can I do that? Yes, because this is also a p-series. I could bring that negative outside there, and I still know this part diverges. That negative just means it's going to diverge to negative infinity. Now, is that true? Well, if you're not real sure, let's cross multiply and find out. So we would have negative 1 times the square root of n. Is that greater than negative 3 minus the square root of n? Well, if I subtract this, I would have this statement. So this is always true. Okay. So that means that this series diverges. What does that mean? It means you do not include negative 1 because negative 1 would make the original series diverge. So now we have to check the other endpoint when x is positive 1. Okay, so remember, we're coming back up here, and where there's an x, we're putting in positive 1. Okay, so 1 to a power, that's just going to be 1, so we can kind of ignore that. And now we do have an alternating series because negative 1 to the power of n, that is going to alternate. So let's use that alternating series test. So first part, does the limit as n approach infinity, remember the non-negative part, does that equal to 0? Yes, it does. And is it eventually decreasing, as in is 1 over 3 plus the square root of n plus 1, is that less than or equal to that? Yes, it is. So this converges by the alternating series test. What does that mean? It means you would include the 1 as part of your domain. So the original series converges for negative 1 less than x less than or equal to positive 1. In other words, we would have parenthesis negative 1 positive 1 bracket. So that would be the domain at which our original series converges. Again, just some more practice. Try it out, then come back to the video. So we have 3x minus 2 to the n plus 1 over n plus 1. So reducing, that leaves me 3x minus 2. So I have the limit as n approaches infinity of 3x minus 2 times n over n plus 1. When n approaches infinity, that value is going to go to 1, so this equals to the absolute value of 3x minus 2. So that means this series will converge if this is less than 1. This is where you need to be careful. Listen, that means that is sandwiched between 1 and negative 1. You really need to write this inequality. Then you need to solve for x. Write the inequality, then solve for x. So if you add 2 to each part, then divide by 3, that's the interval. Then we have to check these endpoints, 1/3 and 1. Can't emphasize this enough. Okay, so we're going to check when x is 1/3, and we're going to check when x is 1. So remember, we're plugging in 1/3 for x. So we would have 3 times 1/3 minus 2. And then we would, over here, we would have 3 times 1 minus 2. Those are the two series we need to see. Do these converge or diverge? All right, so this is 1 minus 2 is negative 1. So we have negative 1 to the n over the nth power. This is 3 minus 2, so this is positive 1 to the nth power over n. Well, I think I'm going to do this one over here, because 1 to the n is just 1. That's just a p series, where p equals to 1, and we know that diverges. So we would not include 1. What about this? It's an alternating series. So we would say, does the limit as n approaches infinity of the non-negative part equal to 0? Yes. Is it decreasing? Yes. So this converges by the alternating series test, which means we would include 1/3. So our interval of convergence would be from 1/3 to 1, including 1/3. The best way to get better at these is to practice, practice, practice.